Hello, welcome to our tutorial. Today, I will take you through design of two-way spanning slab panel. Now, from our diagram here on our left-hand side, we are going to design slab panel G. Now, looking at slab panel G, you find that it is at the extreme end and two of its edges are discontinuous. Now, the condition for slab panel G will be two adjacent edges discontinuous. This edge here is the end edge and this one is the end edge. So our condition will be two adjacent edges discontinuous. Now we have to assume slab G has a measure of 5570 by 7470 millimeter and a thickness of 162.5 millimeter. Then we'll take a top and bottom covered reinforcement of 25 millimeters. We have to compute our effective depth. Now for short span, effective depth will be equivalent to total thickness 162.5 subtract the cover, which is 25 millimeter, subtract, now we shall use 10 millimeter diameter bar, subtract 10 divided by 2, you get 132.5. For the longer span, it will be total thickness, subtract cover, subtract diameter of bars. In the short span, subtract diameter of bar divided by 2. Now we are assuming when you are computing longer span, you already have bars in the shorter span. That's why we have we subtract diameter of bar and another diameter over 2 in a long span. Now we go to loading. Loading, we know we have dead and imposed or live load. Dead load consists of self-weight and finishes or load which does not change in size and direction of action. So self-weight, we know we take thickness multiplied by the unit weight of concrete or density of concrete, which is 24 kilonewton per cubic meter. So you compute and get 3.9. Then finishes, you can take it as 1 kilonewton per square meter. Then imposed load or live load is normally taken depending on the intended use of the structure. For our case here, we are taking 1.5 kilonewton per square meter. Then we can now compute our design load by saying design load N is equivalent to 1.4 times dead load plus 1.6 times imposed load, which will give us 9.26 kilonewton per square meter. Then we go to bending moments. Now, bending moment, now we said our slab is two-way, but we have to prove by calculating the ratio of the longer span divided by the shorter span, which is 7470 millimeter divided by 5570 millimeter, you get 1.34. So we can say slab is a two-way spanning because the ratio is below 2. Now we go to table 14. We'll go to table 14 so as we can now get the moment coefficient. Remember, the short span continuous edge moment is given by this coefficient multiplied by the design load times shorter span squared, the same to this. So this coefficient are obtained in table 3.14. Now, for you to obtain this coefficient, we need two things. One, we need the type of panel. We said two adjacent edges discontinuous, and then we need the ratio of Ly, Lx. So this is how we'll obtain. We'll come here. Now this is the type of panel. We have interior panel, one short edge discontinuous, one long edge discontinuous, and then for short span we use all this area is for short span. Long span has only one column here. And for long span, we don't consider the ratio Ly over Lx as indicated here. Now, our panel type is two adjacent edges discontinuous. Now, it is, now we shall use this particular column, this one. This is our area of focus. And then we know that our ratio is 1.34, which means it lies somewhere between 1.3 and 1.4. This is now where will be our area of operation. So this is the area of focus. This is our area of focus. Now, to start with, we'll come here and say, for the case of BSX, we shall say if 1.3 is 0.069 and 1.4 is 0.074, what about 1.34? Using interpolation, we'll find that now the value of 1.34 must lie somewhere between 0.069 and 0.074. That's why after interpolation, you get the coefficient as 0.071. And then for short span at mid, we come here, still in this table, positive moment at mid span, we move along that direction to where we have 1.34. So 1.34 is not in the table. We look at 1.3, 0.051, 1.4, 0.055. So what about 1.34? Using interpolation, we find the value is 0.053. And then for longer span, here we need these two values. For longer span, we said you don't consider the ratio. For longer span, I'll move along two adjacent edges discontinuous. I move along that. And the last column here, this one, this column, last column here, I take the coefficient is 0.45 and 0.045 and 0.034. These are now the coefficients you've taken. Enough from there, we can compute now the moment for each particular section, because you only take the coefficient multiplied by design load times short span squared. That is how we came up with this particular bending moment for each section. And then from there, now we can go to design of reinforcement. Now for shorter span, each place you consider its bending moment. For shorter span, continuous edge, we say K is equivalent to moment divided by FCU BD square. We substitute, remember this 10 power 6 is to convert the unit from kilonewton meter to Newton millimeter. You get that. Then we compute the arm, which is Z, by using the formula as we explained in the other tutorial. You get the value you get should be not more than 0.95 D. If you compute and get more than 0.95 D, assume Z is equivalent to 0.95 D. From there, we will proceed and calculate steel area, reinforcement area, which is given by that. And now you substitute, you find it is 371 millimeter square per meter. Now from here, we'll go to our table of reinforcement and read. Now we are looking for a value, an area which will give us 371 or slightly more than that. But now the spacing of the bar should not exceed the maximum of, which is 3 times the effective depth. So when you go to the table, look for a value equivalent to 371 or slightly more than, and also the spacing should not be more than 397.5 millimeters. So when we come to our table here, now remember we are moving along diameter of 10. Our diameter is 10 millimeters per. So I'll come this direction here and say along 10, I will move along 10. So we have these values here. Now for this case here, we'll pick, for our case here, we'll pick a value of 393. So 393, it means 10 diameter bars placed at 200 center to center, because we said you also have to meet the criteria for the maximum allowed spacing. And that is why we have now 393 millimeter squared, but now you provide T10 at 200 millimeter center to center. Area provided is that. And then Maximum spacing we compute as 3 times effective depth, which will give us 397.5, and we provided 200, so it is okay. Now we check for the minimum area. Minimum area should be equivalent to 0.13% BH. So we can test. If we test it, we substitute, you find our percentage area is 0.24%, which is greater than the minimum 0.13%, so it is okay. When you go to short span, the same will apply. We calculate the value of K by taking the moment at the short span, mid span. We divide by FCU, concrete strength, times BD squared. You find the value of K. We substitute to compute for the value of Z. The now steel area we get, it is 277. So if it is 277, now we'll go to the table, look for an area equivalent to or slightly more than 277, but where the spacing of bar should not be more than 3 times the effective depth, 397.5. Now, for our case here, now you move along 10, we took the value of 349. I know we have 286, which also meet because it is 277, 286 will qualify, 314 will qualify. The reason why we are picking 349, we find that sometimes the criteria of deflection might fail if you take an area very close to the calculated area. So we'll take 349 millimeters squared per meter, which will be 10 diameter bar spaced at 225 millimeter center to center. So we'll have 349, 10 millimeter diameter bar spaced at 225 millimeter center to center. Maximum spacing, that one we meet. Then now we calculate minimum area. Minimum area should be 0.13%. Ours is 0.21%, so it is okay. It meets the criteria. Then we go to long span, continuous edge. We substitute the values of moment and the other parameter. You get that. You compute for Z using the formula, and then you compute for steel area. So this steel area, you get 254. So you have to go to the table and obtain this particular value. But remember, you have to obtain the value, take care of the value, and also the maximum spacing. Now from the table, you move along 10 diameter. So you'll find that we picked 314, which will give 10 diameter bar at a spacing of 250 millimeter center to center. So we have that. So you use twisted bar, 10 millimeter diameter, placed at 250 millimeter center to center. Then the maximum spacing automatically is more than what we provided, so it is okay. We check the minimum area, 0.13%. Our area passes the test. Then we go to long span, the same will apply. You will substitute the moment along the long span as calculated using the moment coefficients. You get 192, and then we go to the table to obtain an area which will satisfy steel area and also satisfy maximum spacing. So here we also came along 10, so we picked 314. The reason I told you sometimes we pick a very high value is because we also need to take care of deflection. During deflection test, the area provided plays a very vital role in making sure that the deflection test is passed. But you should not over-reinforce because it will be uneconomical and it can cause crushing failure because the crushing strength value of concrete will be exceeded before the steel yield. So we took 314, meaning provide T10 at 250 center to center. Then now we have to test the minimum area criteria. It has been passed because 0.19% against 0.13%. Maximum spacing criteria passed. Then we go to check for deflection. Now for deflection, we only check for mid spans of the short span and mid spans of the long span. Now I want you to understand two things. When we talk about deflection, deflection will only occur at the mid-span, the free hanging part. But when we are checking for the shear force will occur at the support. So we only consider the support or continuous edge. Where we have continuous edge, it means there is a support there, so we shall have a shear force. But where the span is hanging, we call it the mid span, we shall have the deflection. That is why when we are talking about short span deflection, we are using the moment in the short span, mid span, not continuous. Now we will calculate this m over bd squared because we shall use it in our formula here. That's why we are computing it. You compute and then you compute service stress. Service stress is given by 2 times strength of steel multiplied by the area required. Area required is what you calculated, and then 3 times area provided. Area provided, it means the area we read from the table. For our case here, for the short span, mid span, the area we required was 277 millimeters squared, but the area we read from the table was 349. So surface stress will be equivalent to 243 Newton per millimeter squared. Now we can compute modification factor. Modification factor, this is table 3.9. Let me show you. This is a modification factor. So this is the formula we are using. So you can opt to read this value or you calculate, but calculation will be much easier because of a lot of interpolation. So this is the formula we are applying here. This is the formula we use to calculate surface stress. This is now the formula for modification factor. Now, we can now substitute in this formula here where we have Fs, we replace with 243, where we have m over bd squared, we replace by 0.87. So we find modification is 1.67. We know that basic effective depth from table 3.9, it should be 26 because of the continuous slab. Now, allowable will be given by the basic ratio multiplied by the modification factor, which is 26 times 1.69. You get it is 43. Now, the actual span effective depth is, the actual means we take our value. For the shorter span, we know that the span is 570 millimeter and the effective depth is 132.5 millimeter, you get 42. Now, since 42 actually less than permissible or allowable, we say deflection is within allowable limit. We now consider deflection along the long span, but at the mid span. So deflection, we use the moment for the long span, mid span. We compute m over bd squared following the same procedure, calculate service stress, which will be given by that area calculated over area provided, which is read from the table, steel area table, and then you get the service stress. We calculate modification factor here, which is equivalent to 2. Remember, the modification factor should be a maximum of 2. If you get 2.1, you reduce it to 2. Now, basic span effective depth is 26 because it's a continuous slab. Then allowable, you take basic multiplied by the modification factor, which is 52. Now, the actual will be the span 5570 divided by effective depth 122.5, which is 45. So here we send the deflection is within allowable limit. So deflection is passed because allowable is more than actual. Now we'll go to shear. Now check for shear like I told you. Now shear here we look at the continuous part, continuous or at the support. Shear will only occur at the support, but bending moment, highest bending moment will occur at the mid span. Now shear the support here, we shall use table 3.15 like we did for the moment coefficient. Now to obtain this coefficient in red, we use table 3.15. See how we use it. We'll come here. 3.15 is here. I'll come and say my panel type is 2 adjacent edges discontinuous, and we are saying we are using continuous edge where we have the support. So I will move, and our ratio, my ratio was 1.34. So I will move along this continuous edge, and where I have my 1.34. As we did for the moment, you find if 1.3 is 0.5 and 1.4 is 0.52. What about 1.34? Using interpolation, we find 1.34 will give us 0.51. So we multiply by the design load N times the span times 1 meter width to get shear force in kilonewton. Now, the shear stress, design shear stress, we know it is shear force divided by the area. Area is given by breadth times effective depth. So we convert this one to Newton by multiplying by 1,000 or 10 power 3. We divide by BD, you get 0.2 Newton per millimeter square. Now, concrete shear stress is calculated using this formula. It is found in table 3.8. Table 3.8 is here. Now this table 3.8. Now this table 3.8, if you have effective depth of 125, 150, 175, and 200, you can be able to extrapolate value from this particular table. But our value does not coincide with any of this, so we use this particular formula here to calculate. This formula here, we start with 0.79 into 100 AS over BD. Now we'll come and use the formula here, 0.79, and now we just substitute. We substitute the value. Now, when you substitute, you find that the concrete shear stress, what the concrete can carry is 0.58, but what is provided from the loading is 0.2, meaning the concrete does not need shear reinforcement, does not need help to withstand the shear. So we say hence no shear reinforcement is required. Now, for the long span, we also look at the support or the continuous edge. You find that now, going back to the same table, you go back to the same table, you find that looking at two adjacent edges discontinuous, you move along the continuous, you find it has a value of 0.4. I told you for the case of long span, you use the last column, so 0.4. Now this is 0.4 in red, you multiply by the design load times short span times say 1 meter width, you get 20.63. Now you calculate the shear stress. Shear stress is given by shear force over BD. You get that. Now concrete shear stress, you use the formula here, you substitute the component and you get 0.58. Now it is greater than 0.17, meaning we don't need shear reinforcement. Thank you for your time. Thank you for listening. Please subscribe, like, and share my YouTube channel.